Science on Surfaces.
Welcome to this podcast. Today we will talk about surface tension. We will talk about what surface tension is, when and why it's important, and how to measure it. So here with me in the studio I have Susanna Lauren. She's an expert on surface tension and related phenomena. Susanna's been working at Biolin Scientific around these topics for around 8 years, and before that she did her Ph.D. on microfluidics and superhydrophobic surfaces, which are very much related to this as well. So welcome.
Thank you for having me.
It's great to have you here. So let's start with the basics. What is surface tension?
So, surface tension is a property of a liquid. So, the surface of a liquid behaves almost like an elastic sheet. And this comes from molecular interactions at the surface and more precisely, cohesive forces that affect between molecules.
And cohesive?
Cohesive, yes.
Is... can you define that somehow?
So, cohesive forces are between two similar molecules.
Okay.
And then we have adhesive forces, which is between two dissimilar molecules. So, cohesive forces are in the liquid. So, when we have, let's say, two water molecules interacting with each other, that's cohesive force. Mm-hmm. So if we think about, let's say, a glass of water, for example, we have at the surface we have molecules that they have similar molecules on their sides and at the bottom, but then on top they have air molecules. Mm-hmm. So then we have cohesive forces between the water molecules, but then we have adhesive forces between the water and air molecules.
Okay, I see.
So then at the surface, these molecules are pulled towards each other. Basically, they are pulled to the sides and to the bottom, basically more strongly than upwards. And that is where the surface tension comes from. Mm-hmm. And the stronger these cohesive forces are, so let's think, for example, in water, we have hydrogen bonds, which are very strong bonds. Those the surface tension of water is then higher than, for example, in oil, where we don't have that hydrogen bonding and the strong bonds between the two molecules.
Okay, I see.
So if you have probably seen an example where you have a water strider walking on top of the water, and that's because that can happen because of the high surface tension of water. If it would be oil, that wouldn't happen. The water strider would not be able to walk on top.
So then you're saying that water has a very high surface tension compared to many other liquids
absolutely.
Or fluids.
Yeah, it's actually the highest. Then there is a higher one, which is mercury. But that's kind of not something that you encounter every single day. But water has a really high surface tension compared to most of the liquids.
Okay, so when or why is surface tension important, or is it important?
Yeah, it's actually really important. I mentioned the water strider, and you might not really think of it, but it's actually very important to our ecosystem that the water striders are able to walk on top. If we wouldn't have, if the surface tension would be much lower in water, then what would happen is that nothing would really float on the surface, so they would just sink on the bottom of the seas, of the lakes, for example. So it would be very detrimental to our ecosystem if that would happen. And also if if we wouldn't have surface tension at all, then the water would basically just evaporate.
Oh, okay.
So, but if we think about a little bit more like real life situations, we could, the high surface tension of water is actually very problematic to many in many industrial processes. So if we take something really simple like washing clothes, for example, you have probably all noticed that it's very difficult to get a stain off from the fabric just by using water. I mean, it's not able to penetrate and dissolve the stain. Then your first thought is like, okay, so let's use hot water. I try a little bit higher temperature, and that's actually in the right direction, because the higher temperature will decrease the surface tension of water.
Oh, okay.
So it's actually easier for water molecules to penetrate. Okay. But even that is not really enough, and that's why we use laundry detergents that contain surfactants.
So you're saying that you can affect the surface tension by temperature,
yes,
and by adding surfactants.
Yes,
so,
exactly.
So how does it work with the surfactants?
So basically, surfactants are surface active molecules. They have hydrophilic and hydrophobic parts. So they basically arrange themselves at the air-water interfaces, so that you have the hydrophobic part in air and hydrophilic part in water. And when that happens, I mean, they kind of go in between those water molecules. And you remember that the water molecules had really high cohesive forces between each other. But now we are putting basically a surfactant in between. So then those forces at the surface will become weaker.
Okay.
And I mean, these surfactants, they can be anything. They can be polymers, proteins, or even particles. You can go to the surface and decrease the surface tension. And then, I mean, how effective the surfactant is meaning kind of how much it can lower the surface tension, is something that is studied a lot in industrial setting.
Okay, but you're saying that you could tune the surface tension by adding a certain molecule.
Yeah, yes, absolutely. And then it depends on which application areas you are, like which type of molecules you would add. I mean, in food industry you would add maybe proteins. So yeah.
Okay. And how can you measure it?
So there are basically two different methods that are used. So we have two technologies. We have optical and force tensiometers. And I mean, optical tensiometer is, you basically have a light source, and then you have a camera, and in between you have a needle where you have your water droplet coming out. And you can probably kind of imagine that higher the surface tension, bigger droplets you can make.
Because you have this elastic sheet surrounding or
exactly,
holding the drop.
That is kind of holding it together.
Yeah.
And then, I mean, it's all, of course, done with the software, but basically the software is able to then fit a curvature around that droplet, and then is able to kind of calculate from how big of a droplet you are able to make, of how high the surface tension is.
Okay.
Then the other technology, force tensiometry, is based on the very sensitive balance. So you basically have an instrument and you have your sample in a cup, and then you hang some kind of a probe. Usually it's made of platinum on the balance, and then you immerse that probe on the liquid, and then you kind of try to pull that probe up from the liquid, and then you measure how much force is needed to pull the probe.
Okay.
And then, of course, the higher the surface tension, then more force it will affect on the probe, and higher the mass that is measured by the balance.
Oh, okay.
So this is something that is maybe more traditional way of measuring.
Is it important? Tension. Like you mentioned platinum, is that?
Yes, it's very important that to choose the material that is wetted completely, meaning that we don't have any contact angle between the probe and the liquid, so that it pulls the liquid up easily. So that's very important.
Okay, so and there you would have the adhesive force.
Yes,
right?
Exactly. Yeah, that's true. Yeah, that's true. Yeah.
Okay. So if you compare these two, how long do these measurements take typically?
I mean, they are typically very quick to do. I mean, maybe optical method is even a little bit quicker, but I mean, we are talking anyway about minutes.
Oh, okay.
So but then of course there are some situations where you would really like to. I mean, you would like to measure surface tension as a function of time. So if you think about, for example, when you have those surfactants in the liquid, but I mean, it might take a while for surfactant molecules to actually come to the air-water interface. I mean, if you're making a drop at the end of the needle, you are creating that interface at that moment. So then it will take a while for the molecules to actually arrange themselves at the air-water interface. So then you might need to, I mean, you might want to actually measure as long as you can see that the surface tension is stable, because that's actually the surface tension of the liquid.
Oh, so measure until it has stabilized.
Yeah, until it has stabilized to a certain value, basically. Yeah.
And how long? I mean, what would be a long time for that?
I mean, I would say, I mean, I know that some people are measuring like hours.
Oh, okay.
But it's you can usually see in the curve that it's way too long. I mean, usually it takes like 30 minutes or something maximum. I mean, it depends on the size of the surface active molecules, like how long does it take for them to kind of diffuse on to the interface. So
what about evaporation in that period?
Yes, I mean, that's absolutely something that you need to take into account. So then there are different ways of then doing the measurement so that you can get around that. But yes, of course, you can't have a droplet hanging at the end of the needle for 3 hours. No. I mean, it will evaporate. Yeah. So yeah, there are other ways to go around that then.
So I was thinking about situations where surface tension is relevant. You already mentioned like a cleaning situation. Are there any other situations where this would...
I mean, it is actually very relevant anywhere where you would have surfactants in your liquid. So we can go from food industry, as I briefly mentioned, paint manufacturing. I mean, in paints there are a lot of different type of additives that you have to add to the paint to get the consistency. And even in oil industry there are a lot of, I mean, whenever you have basically interfaces between liquid and air or two different liquids, so then it's meaningful.
But if you take the paint scenario, why would it matter?
I mean, you want to, there are several things, of course. I mean, if you have a paint that is composed of different substances and you want to be able to have them, I mean, the paint has to be like one solution. It can't be like something and then something else on top.
Yeah,
and I mean, actually, when you buy a paint, you have to kind of mix it.
Yes,
because they will separate to some extent. But then you need to be able to mix them back as one. Otherwise, you will have your walls looking very weird if you have different oils and waters. So I mean, you have to have them together. So that's kind of what is why people. And I mean, of course, there are other issues as well. I mean, how well the paint will actually spread on the surface.
Okay.
I mean, that's a little bit out of the scope here, but then, I mean, of course, the surface tension of paint affects there.
So the surface tension is related to the paint behavior, both as a solution or whatever.
And on the surface.
And on the surface.
Absolutely, yeah.
Okay. I don't know, could you take like a case example? Is it possible? Or
I mean, we talked about clothes. I mean, washing clothes already. I mean, that's one area where people are or industries are looking for new solutions, because I mean, if you wash your clothes, there is a big need to be able to do that in lower temperatures. I mean, there are two reasons. One is, of course, to save energy. And then the other one is that, I mean, if you can use, let's say, just 20 degrees, it will actually wear your clothes much less than if you need to use 60 degrees.
Right.
So then there are companies that are developing these detergents that need to develop new surfactants that are able to operate at those low temperatures.
Of course.
So, and I mean, this goes with all surfactant development as well, in the sense that, I mean, some surfactants are actually really bad for environment. So to make surfactants that are more environmentally friendly, that's also a very big topic. So, I mean, there are a lot of examples. Then we can also look at the like very simple thing to look at in industrial setting is how much surfactant you have to use.
Mm.
So that's also an environmental aspect and also a cost issue, because I mean these surfactants, they can be actually very expensive. So how much you have to add that surfactant to lower the surface tension. I mean, less the better, both from an environmental perspective. I mean, if you think that they are toxic, so of course if you can use them less, that's good. And then also on the cost side, I mean, if they are expensive additives that you need to add, so you want to use as little as possible. So that's something that you can then measure with the, like, how much do I have to add? Because at some point you will reach, when you're adding more surfactants, at some point you will reach the level where it doesn't affect the surface tension anymore. So
is that the level that you're looking for?
Exactly, yes. So basically you can call it like CMC measurement, so it's critical mass or concentration measurement, without going into the details of that measurement. But basically what we are looking at like how much surfactants should we add to reach that lowest possible surface tension.
And then after that it doesn't change anymore.
It doesn't change anymore, exactly. So
okay, so that's what you're looking for. So are there any particular challenges involved in these measurements?
I mean, of course, there's always just challenge when you are using measurements. So one is high viscosity. So people, I mean, we have been talking a lot about water, I mean, adding surfactants to water. But then there are a lot of different processes where you would actually want to measure something that is not anymore water. It could be oils, and then the viscosities can actually be really, really high. And then I mean, both optical and force methods, they are based on the idea that there's some kind of a flow of liquid. I mean, you need to be able to push it through the needle so that you can form the drop, or you need to be able to pull it up with the platinum probe. So you need to have that flow. I mean, there are some ways. I mean, we can, by changing, for example, the tip of the needle that we are using, we can a little bit affect on how high viscosities we can measure. But I mean, I have even heard people wanting to measure things like peanut butter.
Oh.
So you would never think that a peanut butter would be even a liquid.
No.
And then it's, I mean, to be honest, I don't know how you could measure peanut butter. I mean, it starts to be a bit too thick.
Yeah. Okay, that's fascinating. But then how would you address the viscosity challenge? Is there a way to address it, or will you just, I mean, you can't measure it?
Well, yeah, I mean, there are some things that you can do. So as I mentioned, you can think about the different, sizes of the tips that you are using, and even the shapes of the tips, and maybe the material that you are using. But I mean, there is some limit. It's really difficult to say, because it's not only depending on the viscosity. There is also like the density issue, like how dense is the liquid. So you can't really tell like exact limit that this is the viscosity that you can go to. So it's really, I mean, you need to test.
Of course.
Yeah.
So, and these are the biggest challenges, or are there any other?
I mean, I would say they are maybe the biggest. Then, of course, there are a lot of these. I mean, we need to think about when we are measuring, especially the water-based solutions. I mean, this is very sensitive technique. We need to look at, I mean, if there's any kind of impurities
of course.
in the liquid.
That would have an impact, of course.
I mean, the impurities, whatever they are, they would actually behave exactly like surfactants. So they would also go to the interface and lower the surface tension.
Okay.
So when people take if you take clean water, let's say you take the tap water, I mean, I can't tell you what kind of surface tension you will get from tap water, because I have no idea what kind of tap water you have here in Sweden, for example. So, and it can be very different from what you have in some other countries. So the surface tension value will definitely be different. So you need to be very careful that you know what you're actually measuring, and you're not adding any unwanted impurities into your liquids that you are measuring.
I see. Yeah, and that's not something that the measurement method can do anything about. It's more like a sample preparation.
No, exactly. Yeah, I mean, it's kind of meant to detect that that impurity, so you can't get rid of it in that sense.
Yeah, it's certainly a challenge for the user.
Yes, I mean, of course. I mean, you just need to be sure that you know what you are measuring. Absolutely.
Anything else that is challenging?
No, I mean, of course, then we talked a little bit about the temperature, so you need to take that into account. So, I mean, if you want to be very, very precise with your measurements, I mean, that's not something that you necessarily always have to do when you are measuring, but in some cases, I mean, if you measure at 20 or 30 or even higher, let's say 50 degrees, then, I mean, there is a slight effect on surface tension. So then that's something that you might want to consider if you start to see that, why do I have this variation from day to day? I mean, it could be an issue. And then, of course, I mean, now that I come to think of it, air conditioning.
Oh.
And I mean, the flow of air. I mean, if you think about the droplet of water hanging at the end of the needle, if you have a lot of airflow around, you will just see it in a droplet shaking at the end of the needle. Or if we think about the force system, you have very, very sensitive balances. So if somebody is jumping in front of the instrument, the balance can detect that. So I mean, you need to think about, of course, also a little bit, I mean, which type of environment you are doing the measurements, especially if you want to be very, very precise.
Yeah, of course. And I think in particular then if you do those 30-minute measurements.
Yes, absolutely. Then you need to, I mean, you mentioned also the evaporation. I mean, that's something that we can kind of come around. But yes, of course, that's something that you need to consider.
So what about the future of these measurements? Will it keep being important, surface tension?
Yes, I mean, I think so. I mean, it's so fundamental measurement, and it's fundamental property of the liquid, and it is really so. I mean, when you add surfactants in the system, that's basically what you are trying to gain. You are trying to gain that reduction in surface tension. So of course you have to measure it. But then I would say if we think about the two methods, I mean, the force tensiometry has really been the method that
this was the one with the platinum.
Yes, yeah. Exactly. So this is, I mean, this is really the method that people have been using in the past mostly. And there are various reasons. I mean, one is that it's the older method, and in that sense it has been maybe a little bit more established. And then if we think about like standards, we actually have standards that are using, I mean, how you measure surface tension of liquid by using force tensiometry.
Oh, okay.
So you can, there actually hasn't been so many standards for optical method. But now we have started to see those one as well. Okay. And I actually think that the optical method will probably start to be the dominating one in the future. I mean, there are a few things that are kind of talking for that method. And one is the fact that it's so easy to control the contamination, because you can use disposable tips, for example. You take the small amount of your sample into that tip that you can be sure that it's clean, and then you make your measurement. Whereas with the force tensiometer, you have the measurement cup, which has to be cleaned. Then you have your probe, the platinum. So the cup
is where you have your
solution.
Where
you have your solution, basically.
Yeah,
so if that's dirty, then your solution will be dirty.
Of course.
And then the platinum ring or plate, what you're the probe that you're using for the measurements, you need to clean that.
Yeah, of course.
And then also the shape of that probe is very important. I mean, if it's not, if the dimensions change, then it's not, the calculations go wrong.
Oh, okay.
So then those probes can be quite fractal. So that's why people, it's maybe, So I mean, I think for that reason, the optical tensiometry is probably going to be more and more used. You can also use much less sample in the optical method.
Okay.
So if you are measuring, let's say, some biological fluids, for example, you probably don't have huge amounts of those to spare. So then you can take a really small drop. It's basically few microliters. That you need.
Small.
Yeah, and then in the measurement cup, I mean, you need milliliters.
Okay.
So yeah, there are some changes, and I would say that that optical is probably the method for the future, in a sense.
When you talked about the force approach having been used for a longer time, roughly how long time are we talking about? And what is like the time difference between the two?
Well, I think the optical is probably, I mean, they have both been around for decades now.
Okay.
But I mean, I would say probably the force is like from the beginning of 1900. Yeah. And then the optical kind of came a bit later.
Because of course you need cameras and like
yes,
all
I mean cameras and all of that. And with the force, it's really just the balance. And I mean, of course, I don't know how sensitive the balance was at that time. I mean, it's very high technology in the modern instruments at the moment. But yeah.
Okay, thanks. Learned a lot.
Good.
So I think that's what we had for this episode. Thanks for listening to this episode with me, Malin Edvardsson, and Susanna Lauren from Biolin Scientific. And I would also like to take the opportunity to mention to those of you who are listening or watching that if you're interested in surface science and related phenomena, you should check out our blog, the Surface Science blog. Thank you.